All right, we're going to start with this. Okay, this is lesson 2 about earthquakes. So we're going to get into how the earthquake power is calculated. So you'll have an idea when you hear on the news that earthquake was 6.2 on the Richter scale. From Science 20, you'll actually know how that's calculated. It's the only class in all of high school where that's taught. So I'm really excited to go over that with you guys. So we talked yesterday how a seismograph is what basically takes in the measurements, the shaking of the earth, and it's a needle, and it makes a seismogram, like a little, like a readout. So a typical readout might look something like this. Something like that. Now, that shows the different waves. So the first type of waves we talked about are P waves or primary waves or push waves. Then the secondary waves occur. Now, there's two things that is used to calculate the strength of an earthquake, but also where the earthquake occurs. And that's the amplitude. So the amplitude is the maximum up and down of a wave measured by the machine. So obviously the more powerful earthquakes are going to have greater amplitude. But also it depends where you are from the earthquake, right? If you're really, really far away, those waves aren't going to be as powerful. So then we're going to be looking at the distance, the time between the P and the S waves. So both of those come together to show where the earthquake has occurred and the strength of the earthquake. It's so cool. Okay. All right, real quick review. Oh, maybe we didn't go over this. Okay, seismology is the study of earthquakes. All right, a seismograph is the device that measures the wave power. Okay, that's the wave power. It's the device. And the seismograph makes a seismogram, the actual readout. Okay, so as a bit of review, as I just said, the time interval between the primary and the secondary waves determines where the earthquake is. And we're going to get into that today. Also, how the time interval and the magnitude or the amplitude determines the strength on the Richter scale. Okay, so it's the difference in time between P and S and how much the graph gets jiggy. Okay, so let's take a look at just some practice data here. So I'm going to get rid of these lines. I'll bring them back. This is seismic data from some kind of earthquake. And I've kind of already labeled maybe where the P wave and the S wave is on this graph. Okay, so if let's march this off. What do you think there? Well, about 11 seconds maybe. The P wave starts. See the time on the bottom here, right? Okay, now the S waves are kind of, it's really nebulous, right? Like maybe there. So maybe, I don't know, 10 seconds, we'll say, and 18 seconds. That's when the S waves start. So what's the difference in time between 10 and 18? It's 8 seconds. Okay. Now, if we go over to, this is just the data that's been gathered over many, many years. 8 seconds is, what would your estimation be, right? So 8 seconds is in between 5 and 10. What do you think? 60 kilometers? Sure. So it's an estimation. Now, that time difference between the P and the S is going to change depending on where the earthquake detection station is, where the seismograph is. Okay. Now, let's go forward. If we had an earthquake and it was saying that it was 128 kilometers away, so that would be, if we looked at here, that would be a difference between the P and S waves of about 15 seconds. The problem is that it could be 128 kilometers in every direction. So you know how maybe you've done that before with those stabby things where they have the point and then the pencil, and you put those down a compass and you draw a perfect circle? That's the problem with only having one station, is it could be 128 kilometers in any direction. Now, obviously, if this is the West Coast, it's probably more likely that the earthquake occurred to the west, where the big tectonic plates are meeting, not to the east, where it's relatively tectonically stable. But you have to add more stations. So if you get 3 stations together, wherever the circles meet is exactly where the earthquake occurred, the epicenter of the earthquake. So that's why it's important to have earthquake detection sites all around areas that are prone to earthquakes, so you can quickly determine where the epicenter is, where the earthquake occurred. So these other stations, B and C, they drew a circle around using their data, and they found that they were much closer to the earthquake, so their circles are smaller, and wherever the 3 circles intersect is where the epicenter of the earthquake is. And geologists do this on a map. I'm sure you guys have seen map, like 1 kilometer is equal to 1 millimeter, right? Like a map, like a scale, and then they just figure that out on their little circles or compasses. Okay, now this is a very confusing diagram, but I'm just going to go over this one more time because it's a big deal. I'm going to break it down for you. Actually, you know what? I'm just going to start fresh. Okay, all right. I'm going to pull up a circle. Okay, so let's say random geologist person found out that there's, between the P and the S waves, found out that the earthquake was maybe 100 kilometers. But remember, that's 100 kilometers in any direction. I don't think I can, I'll rotate the whole thing. But that's 100 kilometers in any direction. Now, let's say another earthquake station found out that their earthquake, they were way farther away, and they were like 350 kilometers. So now we've labeled it down. There's 2 possible points where the earthquake could have occurred. That's okay. 2 is probably pretty good. But if you have a 3rd station, that 3rd station will have an intersect point. Now, I can't get this. That 3rd station will have an intersect point like this. Maybe this one is 90 kilometers in every direction. Then, poof, you know where that is. Now, why is that important? To assess damage. Work your way back and figure out where those waves came from. Okay. So this type of using the P to the S wave and then a map to drawing circles figures out where the earthquake occurred. Now, how do we determine how strong it is? Well, it's kind of cool. There's these really cool little charts that are made, and all you have to do is take the data from the 3 different earthquakes. So the amplitude of the wave is, in this case, let's just say, remember now, the amplitude is that little graph where it goes, right? And then we measure how high the waves have gone. Let's say the amplitude on this graph, like there's 100 millimeters. They measured the biggest one, and it turned out to be 100 millimeters. Awesome. And then they figured out the distance between the P and the S waves. So this is that same graph, and then here's the S waves. Let's say they figured that out. It was 300 kilometers. Okay, something like that. What you can do on these little graphs, super cool, is you take a line, you start your line at 300, and then you line it up with the amplitude of 100. And where it goes through is the Richter scale, the power of the earthquake. Now, it's probably good to get a second bit of data from another site. Maybe that site was way further away. It said the earthquake was 800 kilometers away, and it had a much weaker amplitude, right? It was the amplitude was much smaller, but still 4.5. So it's pretty accurate, right? It's super cool. I think that's neat. Now, a couple of things I'm just going to leave you with about the Richter scale. Okay, the Richter scale is something called a base 10. So that means every time you go up in the Richter scale, the earthquake gets 10 times stronger. So if you have an earthquake of like 3, which is like the bare minimum humans can feel, I think it said that on a video, and you go to 4, the Richter scale of 4, the power of 4 is 10 times stronger than 3. If you go to 5, 3 to 5 is 10 times 10, 100 times stronger. So that's why when you get up to earthquakes of 8 or 9, right, like if I continue this scale, that's 10 times, 100 times, 1,000 times, 10,000 times, 100,000 times, 1,000,000 times stronger. So that's why earthquakes of 9 are incredibly, incredibly dangerous. Okay, and the difference is, you just have to say, oh, if between 5 and 6, that's 10, 100 times stronger. Whoop. Now this is kind of blurry, but it just shows you the damage, right? Like if you have an earthquake of 3, you may not even know that you felt it, or 2 or 3. Like you may not even know if you felt it. Maybe it like knocked, I just shook a glass or something like that. But as you get up to 7 is where it's probably causing major damage, unless your buildings are built to withstand it. And then you get up to 8 and 9s, which cause death. They're devastating. Some countries that get a lot of earthquakes, like Japan and Korea, like the coastal cities there, they've built their buildings to withstand it because they have earthquakes all the time. Other places in the world aren't built to withstand earthquakes. I mentioned that before. So when you get up earthquakes that tall, the ground sways, and it just causes the entire foundation to collapse, right? Okay, that is earthquakes, and the second part of earthquakes. So we are now done the second part of geology. So for today and tomorrow, you guys are going to be working on the geology assignment for earthquakes and oil and gas. All right, thanks.